Let's talk about derivatives and integrals of power series. So let's say that you have a power series centered at A, and it has some radius of convergence R that's greater than 0. Then we can rewrite this function f of x as a power series, right? So our power series is going to look like C0 plus C1 x minus a plus C2 x minus a squared, and so on and so forth. And the general term would be Cn x minus a to the n power. And this is a power series that goes on forever. Okay, so this Cn x minus a to the n power, that's our general term. The first part of our theorem basically says that this function is differentiable, meaning it has a derivative, on the interval from a minus r to a plus r, which is its radius of convergence. And we can calculate what the derivative is by differentiating term by term. So our f prime of x, that is going to be equal to the derivative of the C0 term is going to be 0 because that's just a constant. And then when you differentiate the first term, or sorry, the second term, you're just going to get the constant C1 surviving. And then when you differentiate the third term, you get 2C2 x minus a to the first power. If we differentiate the cube term, the 3 would come down, so you'd have 3c sub 3, and then you'd have a x minus a. You gotta subtract 1 from the power, so that'd be squared. Okay, so in general, it's going to be n times Cn x minus a to the n minus 1. And that's going to go on forever. So if I wanted to describe this series in general, this series would look like this. We're going to take the infinite sum, but our n is actually going to start at 1, and it's going to go to infinity. And your general term is going to be n c sub n x minus a to the n minus 1. Okay, so this is going to be our power series. Let me highlight that because this is the conclusion, one of the conclusions of our theorem. And I really want to draw special attention to the fact that this series starts at 1. So let me just highlight that 1 right here. Okay, just make sure that the series starts at 1, because when you take the derivative, the constant term gets killed off. All right, cool. So what about integration? Well, we can, instead of finding the derivative of our function, we can find the antiderivative. So we could put the antiderivative of f of x dx. And when you do that, what's going to happen? Well, anytime you find the antiderivative, you're always going to have some constant c, right? And then the antiderivative of the first term is going to be c0 x minus a. And the antiderivative of the second term is going to be c1 x minus a. You got to add 1 to the exponent, so that becomes a squared. You got to divide by what you just wrote, so that's divided by 2. And so on and so forth. If we find the antiderivative of this general term, Cn x minus a to the n power here, then we are going to get Cn x minus a to the n plus 1. We have to divide by the n plus 1. And this series just goes on forever. So if I wanted to describe this series in general, what's it going to look like? I want to make sure I put that constant c there, and then I'm going to get a power series that starts at 0, going to infinity, and it's basically going to be Cn times x minus a to the n plus 1 divided by n plus 1. Okay, so this is the result of our antiderivative. So let me shade in this final answer here, like this. I'm going to be sure to shade the plus c. You don't want to forget that the antiderivative gives a whole family of functions. So regardless, I guess, last component of our theorem is that the radius of convergence, the radii, since we have two new series here, the radii of convergence of the power series in both 1 and 2, those guys are both equal to r. So to summarize, you know what? When you have a power series, your power series is going to be differentiable. We have this interval of convergence, and we can create two new series, f prime and the antiderivative. That is the derivative and the antiderivative, and the radius of convergence for both of these are r. So why don't we look at a quick example? Let's take a look at example 5. I look at example 5. Example 5, this is our function that we're trying to find the power series of. And this is what I want you to notice first. So what we're going to do is we're going to let f of x be equal to 1 over 1 minus x. And another way we could write that is we could basically write this as 1 minus x to the negative 1 power. Okay? And what I want to do next is I want to take the derivative of this guy. So when I take the derivative, I'm going to get f prime of x. In order to take the derivative, I need to use the chain rule, right? The outside function is something to the negative 1 power, and the inside function is 1 minus x. So when I take the derivative of the outside, you're going to get negative 1 times something to the negative 2 power. You got to keep the inside, which is 1 minus x, and then we got to multiply by the derivative of the inside, which is negative 1. The derivative of negative x is negative 1. Okay? So just to emphasize this, I'm going to mention that we use the chain rule. So when we simplify this derivative down, we're going to get the negative and the negative cancel each other out. So this is going to give you 1 minus x to the negative 2, which is really just 1 over 1 minus x quantity squared. So I want you to notice this thing we were just looking for is exactly what the original problem was. F prime is our original problem. So the upshot of this is I can find a power series for 1 over 1 minus x squared by differentiating f of x equal to 1 minus x to the negative 1. Okay? So the great thing about this 1 over 1 minus x is that that is basically the geometric series. So let me just make it explicit down here. I can basically say f of x equal to 1 over 1 minus x. That's actually equal to the summation as n goes from 0 to infinity, x to the n. So if I wanted to calculate f prime, which I do, that is going to be equal to, I just take the derivative. I differentiate term by term. So that's going to give me the summation as n goes from, now remember, our series starts at 1, right? Because the constant term gets killed off. And then we have from 1 to infinity, we're going to take the derivative of the general term. The derivative of x to the n is nx to the n minus 1. And this is exactly what my 1 over 1 minus x squared is. Okay, so let me highlight this answer because this is really what we were looking for right here. We still need to write down what the radius of convergence was. Remember, we just differentiated the geometric series. So we know that the geometric series has a radius of convergence equal to 1, and its interval of convergence is from -1 to 1. So taking the derivative does not change the radius. So we have the same situation as before. All right, everyone, take care.